So back over here in const vector iterator, I defined a function operator bool that returns true if the things are in bounds. So if pos is less than 0 or pos is greater than or equal to vector size, right, they are considered to be out of bounds. Or I should say, that should be out of bounds, right? So pos should have to be greater than or equal to 0, and pos should be less than the vector size. That is correct. Yeah, that was a typo. Thanks for catching that. Okay, we're going to pick up from where we left off. So this is one of the key parts about polymorphism, and it's super cool. If you have a parent pointer, you can point a parent pointer to any of the children that inherit from it. If you have this parent pointer, you can only call the methods that exist inside of the parent, right? So any things that are particular only to that child, you can't call. If the method call is a virtual method, the compiler will call the child method if it's pointing to the child, and it will call the parent method, though, if it's pointing to a parent class. This is super duper useful if you want to get different behavior depending on what you're pointing at. So over here, I have a parent P and a parent reference PR, child C, and a parent reference CR to C. So you can also do references to the children as well through the parent. I also have this parent over here. So pointer equals the address of P, p.greet, it says hello. Now if I point that pointer at the child, it's going to say buenos dias, because I'm pointing to an instance of the child at that time. Right? So I'm getting that different behavior depending on what I'm pointing to. And the compiler is able to figure out which method to call depending on what the underlying type is. So I guess we should probably show this off before we keep going. Or we'll keep going and then we'll go back to it in a second. Don't do that to me. So what you're going to hear if you're working with pointers and inheritance, you're going to hear about an upcast and a downcast. An upcast is when you convert a child pointer to a parent pointer, and this is always acceptable because a child is always at least a parent. It always has at least the parent parts. This means that any function that accepts a parent pointer or a parent reference as an argument can also accept a pointer to a child or a child reference at no problem whatsoever. If a function has a return value of parent pointer or parent reference, that reference that gets returned can point to or refer to a child object. The downcast is when you go down the inheritance stream, so when you go from a parent to a child. This can be necessary sometimes if you want to access a particular member of the child, and only the child has that. And this is only going to be okay, though, if the parent is really pointing to an instance of a child. If that parent pointer is really pointing to a parent, trying to cast that parent pointer to a child pointer shouldn't succeed. So again, you might need access to do that downcast to get the child pointer from the parent. You can either use a static cast or a dynamic cast to change the type of the pointer. So you want to use a static cast only if you know absolutely 100% for sure, without a shadow of a doubt, that parent pointer is really pointing to a child, because the compiler does not check. It's just like, sure, I'll transform it into that pointer for you, not a problem. But if you're unsure about what that parent pointer is pointing to, you should use a dynamic cast instead. If you dynamic cast a pointer to like the child type, and it's really pointing to that child, you'll get back that child pointer. But if it's not pointing to an instance of that child, you're going to get back null pointer instead. So you can figure out, oh, this is really what I am indeed pointing to. If you dynamic cast a reference, if it's really a reference to that child type, it will succeed. If it doesn't actually reference that instance of that child, it's going to raise an exception. You have questions here? Yeah. Yeah, we're going to get to examples. We're almost through the slides, and examples are like pretty soon, but we can pop over to one. It's just that the examples tend to require like a lot of different things. So over here, that. Shapes. So this is an example that uses inheritance. So over here we have a shape class. And so some things we might want to be able to do with our shape are we might want to be able to get the area of some shape or be able to get the perimeter of some shape. Ignore the equals 0 for right now, but what it means is that this class is not going to implement these functions. And we'll talk about what that means in a little bit. So over here, we have a rectangle. Would you say a rectangle is a shape? Yes. So we inherit from shape, right? And so we also have new methods like get length and get width, because you can get the length of a rectangle or get the width of a rectangle. That makes sense. And we're able to get the area as well, and we override our parent's method to be able to do that. And getting the area and getting the perimeter are pretty much exactly like what you would expect, right? You know, you return the length times the width. Or the perimeter is 2 times the length plus 2 times the width. We also have a circle. Would you agree that a circle is a shape? Yes, so it inherits from shape. So it also picks up the get area and get perimeter methods. But the way that we calculate these values are going to be very different than the way that we calculate them for a rectangle, right? And for different types of shapes, the way you calculate the areas and the way that you calculate the perimeters are going to be different, right? For example, if we had a rectangle or a triangle, it might be like the area is going to be half the base times the height. And its perimeter is going to be the sum of its 3 sides. So that's why this parent back here, shape, says, you know, these things exist. Every shape should be able to do this, but the way the shapes calculate these values are going to be different. And then for calculating the radius and calculating the diameter of the circle, right, those are the things that are particular only to a circle. And then getting the area is what you would expect. Right? Radius squared times pi, pi r squared. The perimeter is 2 times pi times the radius. Yeah. So do you guys remember what virtual means? My children can override that method if it's marked virtual. If I don't mark it as virtual, my children cannot change the way that that function behaves. Yeah, that's why we have shape here. So technically, this virtual inside the circle is not 100% necessary. I just put it here so that I know that if anybody inherited from the circle, they could also inherit from it. For example, we could have a square, right? And a square is a rectangle. Yeah, right? Square is a rectangle. And so we could have our square class could inherit from rectangle and then do things a little bit differently if it needed to. The only thing that's kind of interesting there would be that, again, I mark them virtual so that the children know that they can override it. It's very clear that these methods are overridable. Not putting it there, they're still virtual, but it's just less obvious to readers of your code. Yeah. The const expression makes the value available at compile time if I really needed it, as opposed to only being available when the program's running. Anything else? Oh, yeah. So the override here means that I'm attempting to override in my parent class the get area function. Now, this is here for 2 reasons. One, to notify people that are reading your code that you are intending to replace the functionality of that function. And the second is for the compiler to double check that it's actually possible, right? If I remove override here, code still compiles, code still works, code's still 100% functional, but the compiler's not doing that double check for me. And so if it wasn't actually possible and I was just accidentally overloading that function instead, I wouldn't know it. So override is always good to add on these functions when you are indeed overriding it. There is no overload keyword to make sure that you're actually overloading the function instead. So we're about to get to that in a moment. Now, you might, So the difference between override and overload is this. I know the words are very, very similar. So override means the child is going to replace the functionality of the parent method, right? So the child is going to do something instead of what the parent does. The overload means that there just happens to be a function with the same name. That's the difference. Anything else? Yeah. So the const behind the function means I do not modify this instance of the class. I won't modify myself. So in computing the area of a rectangle, I am not going to change the length or the width of the rectangle. Right? So when you're marked const, it means you can't change any of your members inside that function. Anything else? Yeah. Protected means I have access to that method, and any of my children have access to those members, right? So if somebody decided to inherit from me, for example, we made a square class that inherited from rectangle, the square would be able to access length and width. But if we made it public, everybody could access it, which we probably don't want to have happen. And if we made it private, none of our children could access it. Anything else? Yeah. So the override means I'm going to be replacing my parent's functionality, right? So over here, rectangle is saying I'm going to replace the functionality of get area and get perimeter of my parent class, which is shape. I'm going to do something different than what my parent does. And the override allows the compiler to check that you are indeed overriding that function as opposed to overloading the function. Anything else? So, yeah. So these methods here are pure virtual methods. It means the parent provides no implementation of that method. And the reason for this is there's no generic code that makes sense for the children to inherit, right? Calculating the area of a circle or the area of a triangle or the area of a trapezoid or the area of some arbitrary shape. Do you know how to do that? No, so the parent's like, I don't know how to do that either, right? I don't have any code to provide you with. But we're going to get to that in 1 second. Right? It's so that when you can have, it'd be nice, let's say, for example, you're doing a drawing program, to have a bunch of shapes, right, on the screen, right? And so you might want to be able to ask each shape, what's your area, what's your rectangle, or what's your perimeter, what's your area, right? And if you don't override that, or you don't have this declared in the parent, the children won't have it, so it doesn't provide this uniform interface. So it'd be nice to have a vector of shapes, right? As it is right now, you can't have a vector of shapes. The reason you can't have a vector of shapes is because the parent class is an abstract class. And an abstract class just means one or more of your methods is purely virtual. Because my parent doesn't provide an implementation for these methods, I cannot construct an instance of that class. Because if I could construct an instance of that class, then I could call those methods on it. But there's no code to run, so it would cause a lot of problems. But if you have an abstract class, you could have a pointer to that class or a reference to that class, just no instances. So what we do over here in main is I have a vector of unique pointers to shapes. I have a vector of shape pointers, right? And I can make those shape pointers point to either circles, or they can point to rectangles, or they can point to anything else that inherits from shape. And if I want to, I could then call with that parent pointer, because you can only call parent methods, I could call get area or get perimeter on that child. So over here, back in main, So I go through this loop. Every even element is going to be a circle, and every odd element is going to be a rectangle. And I make some random circles and some random rectangles in there. So we're going to pause up to line 20. Do you guys have any questions? So I'm using make unique to create a circle. I'm using make unique to create a rectangle, right? I'm getting pointers to circles, pointers to rectangles. And my vector is a vector of pointers to shapes. And a circle is a shape, and a rectangle is a shape. So that parent pointer can point to a circle, or it can point to a rectangle. Yeah? I'm not making a vector of circles or rectangles. Right? Here, I'm making a single circle. I'm making a single rectangle. And that element gets added to the back of my shapes vector. Yeah, so remember, make unique, or like new, it creates an instance of that class, and then gives you back a pointer, if you're using new, or a unique pointer in this case, because we're using make unique to that object. So we're creating a new circle or a new rectangle.
Type shape, because it's one level, or any level deep, as long as they all inherit.
As long as you inherit somewhere from shape, you are a shape. So like if we had something like, again, the square inherits from a rectangle, right? A square is a rectangle is a shape, so a square is a shape as well.
So
well,
rectangles for shape.
Well, again, we'd probably do rectangle because it would make a little bit more sense for the problem, right? But yes, you could create squares then. And your shape pointer could point to a square object because it is a shape. You can point to like any of your children that inherit from you, no matter how far down the line. So you can point to your children, your grandchildren, your great-great-grandchildren, however far down the line, there's no issue because they all are at least whatever you are. But you can only access those things that are made up of you. Any other questions about, these couple lines here? Yeah. Correct. We aren't creating shapes, we're creating circles and rectangles, and we're setting shape pointers to point to those circles and rectangles. Anything else? So, ignore this stuff for right now. Comment that out. So what we can do is we can go through each one of our shapes, and we can get the area of the current shape. I'm not sure where this area comes from. Right, but because each of these, shape pointers can point to the area of, the shape pointers can point to either a rectangle or to a square, we can ask for the area of that current shape. And so when we run, we're going to get the areas of each of our objects, whatever they happen to be. So we made different circles and stuff. Now, I think I probably, okay, the area here was the total area. So down here with this section of code, this is where we're doing the downcast to the children pointer. Right, so I attempt to dynamic cast to a circle pointer, whatever the shape is pointing at, and I also attempt to dynamic cast to a rectangle, whatever that thing is. So if the pointer is not null for circle pointer, what's it mean that I'm pointing to? A circle. And so, I can get the current radius of that circle. If I ask for if the rectangle pointer is not null, that must mean that the current shape is a rectangle, and I can ask for its width and its length. This is the downcast, casting to your child going farther down the inheritance line. And you can see that it's going to alternate. The current shape is a circle with radius 14, then it's a rectangle, then circle, then rectangle, then circle, then rectangle, then circle, because we inserted them in alternating order. And you can see that we're able to get that information back out if we need it. If you're doing a good design, though, you will very rarely need to cast down to a child, because you'll have provided a nice interface in the parent of what method should exist on everything. And then you would, in general, only need to access your children through those methods. Any questions so far about this stuff? Yeah. Yes, you can inherit from multiple objects, and we are going to get into that subject in a little bit. Yeah, so if we wanted to avoid the downcast, we'd have to put like radius and length and width, those member methods, in the shape, but it doesn't really make sense to put them there because not all shapes have a radius or not all shapes have a length. So we didn't put it there. Only things that are, collectively shared by all members of this class should be in the parent. Any other questions? So, yeah. I need a downcast to be able to access the child members. So if I want to be able to access get width or get length, only rectangles have that, right? Shapes don't. So I would have to downcast my pointer to a rectangle pointer if I wanted to be able to access things that only exist inside rectangle. Or downcast it to a circle to be able to access things that only exist inside circles. Yes, so the only thing that we know about shapes is they have an area and a perimeter. We don't know anything more about it. So I have to downcast to the particular child instance to know what I actually have and to be able to access those things, because shapes don't have a radius. Shapes don't have a length, but rectangles do and circles do. Does that make sense? So what do you think would happen if I changed these dynamic casts to static casts? Get an error, fails to compile. It compiles, but it breaks at runtime. Right? So if you're doing this, because we know that when we're going through this vector of pointers, right, not everyone's going to be a circle, not everyone's going to be a rectangle or a circle. But here we said, compiler, don't check, just change it for me. So we're attempt to change circles into rectangles and rectangles into circles. And so when I call those methods, weird stuff happens. So the first thing is going to be a circle, which probably makes sense, but the current shape is also a rectangle as well. Right? The next one is also a circle and a rectangle. Right? Because the dynamic cast will return null pointers instead, but the static cast is just, sure, I'll change it for you. And so now when we start calling these methods, we get some weird behavior when we're calling the circle methods on rectangles and the rectangle methods on circles. Weird stuff happens here. The difference between static and dynamic cast is the compiler checks dynamic casts. The compiler does not check static casts. So if you dynamically cast something and it is an instance of that type, you get a pointer to it. If you dynamic cast it, right, to some type and it's not actually that type, dynamic cast returns null pointer instead. It's not really a pointer to that thing. But if you do a static cast, the compiler's just like, sure, you know what you're doing, I'm going to go change the type of that pointer for you. And it always gives you a pointer to that thing, but of a different type. Any other questions? Yeah. I mean, you can set a circle pointer to point to a rectangle, but what happens when you do that? It's kind of, I don't know, weird, right? We don't know what's going to happen. So you can, dynamic cast does have a little bit of an overhead to doing it, So again, if you're 100% certain that you know from some other way that what you're really pointing at is an instance of the type you're trying to cast to, use static cast. But if you're unsure and it can point to one thing or the other, you have to use dynamic cast then so that you can check to see what it is you're really pointing to. But if you're doing like a lot of these type checks on the dynamic cast, you're probably implementing things incorrectly. You haven't done it right. So what we just kind of saw was with the checking from the types. It is possible, again, to use dynamic cast, but if you have to keep checking, again, you're doing a bad job. The whole point of that polymorphism is so that the compiler transparently redirects the virtual method calls to the appropriate class. So type checking should be limited. If you do end up doing a lot of type checking, ask yourself, why are you doing this? If you're like, well, I want to do something different if it's a this, or if it's a that, or if it's the other thing, right? Maybe there should be some method in the parent class that you can just override in the children to have it go do the different thing for the different types. If you do have a vector of mixed types like we saw before, and you need to know what you really do have, that's a place where dynamic casting makes sense. So again, we kind of already saw these things. Pass, fails. So this is the other thing, the pure virtual methods. So sometimes you have functions in your parent class that you aren't able to provide implementations for, but it makes sense to have there. And you saw that with the shape, right? The get area, the get perimeter. Does it make sense to have the generic parent do something? Because I have no idea what to do for a generic shape. But it does make sense to ask for the area of a shape. Another example might be you might want to be able to connect, right, to some other thing. Like you might want to be able to connect to the internet. And the way that you do that, you might want to be able to do things like start a connection, end a connection, send data, receive data. But the way that you do this is going to depend on whether you're a Wi-Fi connection or an Ethernet connection or a point-to-point connection, right? Each of these things is a connection, but the way that they do their transferring of data or their starting of connections or ending of connections is going to be different. So what we could do is we could declare these methods as being pure virtual. You do that, as you saw with the shapes, by setting them equal to 0 in the function declaration. Any function that you do this to is pure virtual. You do not have to provide implementations for these functions, but your children do, or your children's children, or your children's children. Somebody down the line has to provide an implementation. If your class has one or more pure virtual functions in it, it's called an abstract class. And you cannot create instances of an abstract class. You again can have references or pointers to it. And a class with no pure virtual methods is called a concrete class because you're able to implement it. In this example, all the methods on the right are pure virtual, but you don't have to do that for an abstract class. As long as there's at least one method that's pure virtual, the entire class is abstract. It may make sense for a particular class to have some of its methods being pure virtual and some not, because you can provide some meaningful implementation there. Any questions about pure virtual or abstract classes? Okay, again, why would you bother with an abstract class? It provides a uniform interface. Different children may implement the functions differently, but since they accomplish the same thing, you don't really care how it's done. You could also really easily swap children out if you find a better way of doing things, and you would only have to change a single line of code. If you have that parent pointer that describes this abstract interface, everybody needs to be able to do this, and you have implementation 1, and maybe you find that doesn't do a good job, you can create a different implementation 2, that also inherits from that parent class. And instead of creating an instance of implementation 1, you can just say, oh, equals new implementation 2 instead. And the rest of your code doesn't have to change at all. So again, you make a pointer to the abstract class, prefer smart pointers for ownership, and then dynamically allocate space for the child class. So here we could have a unique pointer to a connection equals make unique Wi-Fi connection. Oh, we want to do an Ethernet connection instead. Unique pointer, right, of type connection equals make unique Ethernet connection, whatever parameters you need to pass. And now con start, con send some data, con close. I don't need to change anything here, right? If I like the Wi-Fi connection, I do this. If I like the Ethernet connection, I can do this. But this code down here doesn't change at all because the children do whatever needs to be done inside of them. And I can switch implementations very quickly, right? I could go from having my laptop plugged in via an Ethernet connection, I unplug it, and then have it switch to be using the Wi-Fi connection instead. No problem there. So you can't have a vector of mixed types, so you can't have a vector of children and parents, but you can have a vector of parent pointers, and the parent pointers can point to parents, and they can point to any of their children. And again, we'll use smart pointers to probably manage the space. So a vector of unique pointers to parents, and again, just like you saw with the shapes, we make one person be a parent, the other person be a child. We would alternate. Again, that parent pointer can point to both. So you can have vectors of mixed types as long as they all inherit from the same parent. But again, your vector wouldn't really be of these mixed types, it would be of the parent pointers. And so you can only access the parent methods that are defined on them. It is possible, as was asked earlier, to inherit from multiple different classes. You're going to get everything that they have, and it's really useful if your class is really one or more things. What you do is you separate who you inherit from by commas. If both your parents do happen to have a member method with the same name, that's okay. It can be a bit confusing though. And if you want to use a parent's members method, you still preface it with the parent's name in front of it. So here we might have an instructor, here we might have a researcher, here we have a professor who's both an instructor and a researcher. And they do inherit a do work method. So you can say, do the instructor's work of your job, then do your researcher work. Does that make sense? So there is some weird stuff when you inherit from multiple things, in that you really do get everything that parent has. So over here, we kind of have this example worked out a little bit. So over here at the top level, we have a person, and the person has a name, right? We have students. Well, you guys are people, right? So you inherit from person, and you're able to just, get the name. We don't override our parents' get name because we want to do the exact same thing, but we still have to provide our own constructor because constructors aren't inherited. Then we have a researcher. A researcher is a worker. Worker's over here. So a worker is a person, and they have the ability to do some work, but we don't know what work they do because a worker is a very generic role, right? You might be a janitor, you might be an instructor, you might be a researcher. How you do your work is going to be very different. So that's why it's pure virtual up here. Then the researcher, they have their do work. They have a field, right? They inherit from worker. And if we pop over here, all it does is it prints out that, whoever there is did some research in whatever their field is. Then we have an instructor. Well, an instructor is a worker. He overrides the do work method. And an instructor has some students. And the instructor over here, right, he teaches these students some subject. And he says, blah, blah, blah. He teaches these students. And again, back here, an instructor also has a string for their subject. Now we have a professor over here. A professor. Yeah, professor, where'd you go? Who inherits from both a researcher and an instructor. He has a name, a field, a subject, and students. And so when we do some work, we say, hey, do my researcher work, do my instructor work. Now, one thing that's kind of interesting is we can't say name, even though an instructor has a name. The reason for this is that name, as you can see, is ambiguous. It's found in multiple of our parents, right? Because a researcher has a name because they're a person, right? And a professor has a name, or an instructor has a name because they're also a person. So you have your researcher name and you have your instructor name. And there's nothing forcing these two things to be the same. which gives some kind of weird behavior because it doesn't really make sense right now, right, for anybody to have two names, right? So probably like one of the things that we did that was poor design is that we didn't just define a pure abstract interface where we only defined methods in the parent classes and just inherited from those and then made the members, like the names, a little bit farther down. So we can't say, name here because we don't know whose name, but we could say, oh, what's our instructor name? And we could see out, oh, what's our researcher name? Also, like, we can't do get name because it's ambiguous, because both of our parents have a method named get name. Does that make sense? Yeah. So like we do have a get name. The question is like, well, if we call get name on that class, whose name would we get? Would we get the instructor's name or would we get the researcher's name? Yeah, so it inherits from both. So like we can point a worker at this professor and we can ask them for what's their name. I'm not sure who's it's going to call. Yeah.
So what's the
Probably what would be better is that if we didn't have worker inherit from person, or because like it makes sense for you to be like both a professor and an instructor and a researcher, but you'd want to make it so that when you designed it, that name member only showed up in one path down the line. So like what you could do is you could have a person and a worker doesn't inherit from a person anymore. And so we could inherit from professor and instructor, professor and instructor and person. But again, still having the get name would be a little bit ambiguous. And there's no more batteries. So back here over in main, right, we create some students. There's Bob, there's Joe, there's Sally, there's Lauren. And then we say we have a professor. He's Mike. He's a professor of chemistry, and his research is in biochem, and he's teaching these students, I believe. Or it's the other way around. He does research in chemistry, and he teaches biochem. So we can say prof.dowork, or we can say prof.researcher, : do work, if we want it to be very explicit. Again, if we do something like prof.getName, that's ambiguous. Do you want to call the professor's, the researcher's get name, or do you want to call the instructor's get name? But we can do something like, oh, get me my instructor name, whatever that happens to be. So I'll comment these out right now so you can see the rest of the code running. Not build all. And this finishes. So you can see that Mike did some research in chemistry, but Jones teaches biochem to Bob, Joe, Sally, Lauren. And you can see that the person's first name, which I think we did, so their instructor name is Bob, and their researcher name is Jones. And the reason for this is because you can see back here in main, well, we passed in their name as being Mike, right? But if we look at our constructor, well, we call the researcher constructor with name and field, and then I just decided to pass in for instructor, their name was Jones. Right, so everybody always ends up with Jones as their instructor name for whatever reason. You could pass in both, name and name, and so now this person has two names, and they're both Mike, but they're Mike twice. So it's, again, really weird for the person to have two names, but that's exactly what happens. Do you guys have questions about multiple inheritance? Yeah. It's not a poor design. We just used it poorly here in this example. Generally, when you're going to be using multiple inheritance, the best way of doing it is defining multiple abstract classes that only have pure virtual methods and no members, no data members. So then you just inherit all their functions, right? And then you have to go implement them. That's the preferred way of doing it. Or again, it also seems weird here because we have this kind of like diamond shape where we join back together. Yeah. So again, like the class doesn't necessarily have to be abstract, right? It doesn't have to be abstract. It could be like a fully implemented class. And again, we might have people that inherit from it and change the functionality of some things. But again, that would allow you to have like collections of the parent type, so collections of mixed values, right? Like a good example of this is, let's imagine we have our tic-tac-toe game, right? Tic-tac-toe game is made up of players, agreed? But you might want to have human players and AI players. But human players and AI players, what are they both? Players, right? Or another example to think about is think about the game of Monopoly. So over here we have our board, right? Because the game of Monopoly has a board. Right? And what would you say a board is made up of? Spaces, right? But are all the spaces the same? No. What types of spaces do you have? We have property spaces. We have chance spaces, like card spaces, the chance and community chest. We have a go space. We have a jail space. We have a go to jail space, right?
Railroads.
What? We have railroads, but railroads are what? Properties, right? So now under property spaces, right, we have 3 different kinds of property spaces. We have the railroad spaces, we have the utility spaces, and you have like the normal ones. I don't know what to call the normal ones besides normal, but you know, the land places, right? So you could have 3 properties under space, right? Now, what you might want to have happen is, well, like a player can land on a space, right? But what happens when they land on a space is going to be different than, it's going to depend on what the type of space is, right? So you can use the inheritance and polymorphism to have in your base space class, like land on or activate or something, and then you can override in your children what happens in each of those methods, so that you're able to get that different behavior. Because like if you land on a property space, you can buy it if nobody owns it, or you pay money to whoever owns it, right?
Pero determining where I am.
Yeah, and so instead of saying like if the space's type is property, else if the space's type is go, else if the space's type is this, right? You just say space.activate or space.landon, whatever makes sense to you. And then that child is responsible for doing whatever needs to happen there. Does that make sense? And then again, with like the different types of like properties, you can calculate the rent differently, right? Because like when you have the property space, like when you land on it, what do you need to do? You know, like if you don't own it, right, and somebody else owns it, you need to pay them rent. But the way that rent is calculated is going to be different depending on which type of property space that you're on. So you could just say, you know, property.calculate rent, and depending on what of these spaces you're on, it would calculate the rent in the correct way, right? So it eliminates all these big nasty if, else if, if I'm this, else if I'm that, else if I'm this other thing. Do the same thing, but a little bit different. That's the power of polymorphism and inheritance. Do you guys have any questions here? Yeah. Yeah. Header file for the professor? So he does inherit, I think the members that he has that he inherits from person is his name, which is protected. So yes, you're correct. He doesn't have any private members, but he does have a protected member that he inherited from his parent, which would be the name. He actually gets 2 names, one from his instructor and one from the researcher. Yes, and we did. So just hold on one more minute. So one pattern that can be really useful for creating different things is the factory pattern, and you can use this to create different children. So what you might do is like say, like I want a unique pointer to base factory, and if which is equal to 1, return child 1 type. Else if it's 2, return child 2 type. So you're able to construct the different children that you want. We'll also show some examples of this on Friday because we will implement different types of players. We might say make player, but make this overloaded, not overloaded, templated. So you might say like make player, and you might say in diamonds make player AI player, make player human player to get the type of player that you want. So one thing that can be really, really easy mistake to make is to put a child inside of a parent. So putting an instance of a child inside of a parent's class, that throws away all the child stuff. This is really easy to do when you pass by parameter, or you pass by value, or when you return by value. So over here I had this bad example that takes in a base B. Notice it's an instance of a B. And I attempt to pass in star BP, where BP is a derived instance of that class. And so now what happens when I pass this function in, it's going to delete whatever the child stuff is as it gets passed into the parent object. Because the parent can't fit the child stuff. So the child stuff gets lopped off. So if you have functions that are going to be working with potential children, have those functions accept references or have them accept pointers. References are preferred though. We will do examples of this on Friday and show some more examples there as well.
Back to the Monopoly example.